So about the Prometheus model, which is actually developed initially in Ethereum Lab of NTUA and is now maintained in Ethereum modeling. And a few, let's say, historic facts is that the actual model comes from similar global energy system simulation models, and they have, let's say, a similar way to deliver the projections, like the poles, for instance, which is used by the Commission, and also the IA's world energy model, which is used for the famous world energy outlooks. So Prometheus is an energy system simulation model and covers in detail both demand and supply, and explores the interactions of the energy system, especially with the environment, the economy, and the policy. It analyzes all these interdependencies based actually on one unified modeling platform with projections up to 2050, where we are currently now expanding to the end of the century. And until now, the model has been widely used for IPCC scenarios, especially the IPCC AR6. We have provided several scenarios there for some energy roadmaps for the energy for the European Commission, especially those that they are the reference scenarios that are usually published by the Commission, and also several multi-sector studies from Horizon projects. So what Prometheus does in a nutshell is that, of course, it's like all models, it has a specific representation of sectors with the granularity, a relatively high granularity, not for instance, it represents several energy demand sectors, but also subsectors and transportation modes. While in terms of countries, it represents a global system split into 10 to 20 regions, because now we are in the process of expanding a bit the regional coverage of the model. And of course, the focus is always on large emitters. It simulates the impacts of specific low carbon scenarios through a specific set of mechanisms that are incorporated in the model. For instance, we have price-driven market interactions between energy demand and supply. The trade of energy can be global and also regional. I will explain later. We have technical progress incorporated, so especially for the low carbon energy technologies, with learning by doing and learning by R&D, and also detailed coverage of policy instruments, especially those related to the energy system and climate policy instruments. So currently we have 14 regions, and this will be expanded more, as I've said. And the focus, of course, is on major emitters. The demand sector, which are one of the key aspects of the model, because demand is fully endogenized in Prometheus. We have 5 main end-use sectors, quite comparable to what traditional IAMs have. I mean, we have industry, commercial, residential, transport, and agriculture sector. But within each of these, let's say, broadly defined sectors, we also have specific subsectors and specific energy uses. So, for instance, in the industry sector, we split some energy-intensive and trade-exposed industries like iron and steel and cement. While also in the transportation sector, we have some coverage of specific modes, like, for instance, aviation recently, and also we have coverage of the passenger road transport, passenger cars, in a sense. The energy supply sectors, we cover the full spectrum. I mean, starting from fossil fuel extraction to fuel transformation, like refineries, biorefineries, etc., electricity production, hydrogen production, and also the heat. And all these, let's say, commodities like energy products, oil, gas, electricity, etc., can be traded at least throughout the regions based on demand and supply dynamics. So here's a simplified flowchart of the model. It has, let's say, all the main sub-modules that we have, starting a bit from the demographic macroeconomic, giving input define, let's say, the final energy demand profiles, which I said are endogenous in the model. While from the other side of the spectrum, we have the natural fossil fuel endowments. So essentially the resources of fossil fuels, but also the resources of renewable energy, which define, let's say, the demand, the supply side. So, and in the intersection of demand and supply, we have the price-driven. So we have the equilibrium between demand and supply, which determines the evolution of the prices of energy products. And usually this is done. This can be done both on the global level, for instance, to simulate the global market for oil, or can also be done, let's say, in a more regionalized sense, like, for instance, to simulate the evolution of gas import price in the EU, for example. And of course, we have this energy, also the technology dynamics, which are the red boxes, which are also quite important in the model, because these, in a sense, try to represent what has happened, and we think that it will continue in the future of the declining costs, especially for some low carbon technologies, but also what can happen in the new technologies that emerge now, like electrolyzers or BECCS, etc. And of course, this influences a lot the mitigation pathways projected by the model. So some specific focuses I have on this slide. The first is the focus on energy supply and demand. So the previous, I made, let's say, a deep dive into the previous chart, and now it focuses really on the energy system, which, as you may see, it covers, let's say, the whole spectrum from fuel extraction to the final demand. So the demand actually for final energy services, like demand for specific industrial products or demand for mobility services. And it encapsulates the whole spectrum of links between the energy resources, the conversion and processing, like the electricity sector that is used to convert the different fuels into electricity, also the grids and storage, potential storage. Also, new technologies are covered, like Power-to-X, which can be seen here, that uses essentially clean electricity to transform into some fuels that can be more easily used by the end use sectors. And in the model, both demand and supply are endogenous and are influenced, of course, by price dynamics. And with respect to the granularity of the model, we have actually, the model is a combination, so I cannot classify either as a bottom-up or a top-down, but uses techniques both from a top-down analysis, for instance, econometrically estimate the elasticities to simulate the demand growth, the demand evolution. And on the other hand, we have a bottom-up detailed technology representation, which is embedded both in supply side, like electricity plants, but also in energy demand sector. Like, for instance, we have very specific technologies for different types of private cars or different equipment in the buildings, for instance. And the second focus is the focus on the fossil fuel market modeling, where actually, in contrast actually to what is done in most of these IAMs, we have quite a good representation of the market. So the price of Brent is not like an exogenous assumption in the model. No, it comes, in fact, as a result of the demand and supply iterations in the global level. So it is actually influenced by climate policies, for instance, because climate policies tend to reduce the demand. So the oil price will also reduce. And we try to be as close as possible to the actual market. So we have one global pool for crude oil, which is usually the main case, with the spot price, actually then influencing the spot prices of other oil products like diesel and gasoline. Of course, later it influences the price of consumers in different countries. But for instance, for gas, we have three regional pools, EU, USA, and Asia, actually, because these three markets are quite distinct in how they price the natural gas. So the prices actually are a result of the complex demand-supply interactions, and also can capture at least potential cartel behavior of producers like OPEC. This is, let's say, a feature of the model which is not always activated, of course, but we can cover. And in addition, production cost of fossil fuels are regionally differentiated. So the model ensures that, for instance, the lowest cost reserves are produced first, and then it's like a marginal supply curve which is followed. And the policy instruments, we mostly work with the carbon price or emission constraints, like most of the models. But on the other hand, we also have detailed policy measures for instance, subsidies on specific technologies or fuels. We can simulate constraints on the availability or the growth rate of particular technologies, the upscaling potential of technologies. We can promote different fuels like renewable energy or limit, for instance, bioenergy, if this is, let's say, in contrast to other sustainable development goals. So in a sense, we can, and also quite important, especially for the EU policy debate, we can also simulate the energy intensity, carbon intensity standards, which are, let's say, most prevalent used by the EU in order to regulate, for instance, the transportation transformation. And some key policy relevant questions that the model has been used. Sorry, it's probably the last slide. So we have assessed the impacts of global hydrocarbon resource assumptions on how the energy and emissions will develop in the EU. So what is the influence there, the interplay between the global fossil fuel price and the transition in the EU. Of course, we have participated in several exercises to analyze the impact of NDCs or low emission net zero strategies by major emitters, and the contribution of the global upscale of good practice policies, and how this can be upscaled towards meeting the Paris Agreement goals. And then, of course, there are several studies, like, for instance, examining the role of specific options, like the role of CCS in developing countries, or the role of demand-side mitigation, like more efficiency towards the 1.5 Paris goals. And for instance, we have also done some studies recently on the green recovery packages and also the use of fossil fuel supply policy. So in contrast, try to reduce demand for fossils like you do with the carbon price, there are also advocates of policies trying to reduce the supply of fossil fuels, which is quite something unique, and we have tried also to analyze that. Of course, the model can cover some SDGs. To be honest, usually quite a lower amount than some of the other IAMs. So we can cover quite nicely, of course, the SDG 7 with regard to affordable and clean energy, and also the SDG 13, the climate action as we simulate, of course, the reduction of CO2 and greenhouse gas emissions. The SDG 8 can be covered. We have done it in the past, but capturing only a part of that. So combining actually the Prometheus output, like technology capacities or fuel use, with some employment multipliers, and try to figure out what is the direct employment created in the energy sector and how is this influenced different pathways. While for the SDG 3, we can, let's say, use the output that we have in terms of solid fuel in buildings, and this can be used for an analysis of local air pollution, while the life on land, afforestation is not covered in the model because we cannot all, but we can simulate some constraints, so land as a constraint in a sense, towards ambitious investment on renewable energy. So we can simulate land-specific constraints on that, and here's a list of recent publications and references using the model.